Right. So hopefully you've already refreshed your probability basics. I won't go through all of those in detail, but maybe I'll discuss some topics which you might have not seen in much detail in your probability course. Many of you may have seen all of these topics, but it's always a good idea to refresh some of these because they're not very introductory in some courses. If you've only taken maybe a 1 credit course, then you may have not discussed this in much detail. So are there any questions related to the topics discussed in the previous class? Okay, so let's get down to it. So whenever you've taken a course in probability, the first thing you start with is a probability space, right? And typically a probability space consists of 3 things: omega, f, and p. So omega is sometimes called the sample space. Sample space. So this is in some sense the set of all outcomes. If the sample space is finite, then this is simply the set of all possible outcomes. For example, if you're rolling a die, then the sample space essentially is all the possible outcomes: 1, 2, 3, 4, 5, or 6. If you're tossing a coin, then there are 2 possible outcomes, head or tail, and the sample space consists of the 2 outcomes, right? So for example, for rolling of a die, the sample space consists of 1, 2, 3, 4, 5, and 6. For tossing of a coin, it is head or tail. Correct. But then one may also be interested in more complicated sample spaces. So for example, if you are, say, measuring the temperature or measuring something which is a real number, then the potential sample space could be the set of all reals, or maybe some interval, right? So if you're measuring, say, the temperature, then maybe it can vary. It can be any real number between, let's say, 0 degrees Celsius to to whatever, say, let's say 45 or something. So maybe in some particular region, the temperature only varies between 0 degrees Celsius and 45 degrees Celsius, and therefore the sample space, no, that is the set of all possible outcomes, can be any real number between 0 and 45. Right? So this is the sample space. But then what we're interested in are not just outcomes, but also possible subsets of outcomes. And that corresponds to the event space. Right? And these are the possible events or subsets of the sample space. Now, if the sample space is finite, so for example, in the case of rolling a die or in the case of tossing a coin, typically the event space in consideration is the set of all subsets of the sample space. So if omega is finite, then you typically take f to be set of all subsets of omega. If omega is infinite, so in particular if it is, say, the set of all real numbers or some continuous interval, if omega is continuous, so in other words, it is uncountably infinite, then F is some subset of the set of all possible subsets. So one reason why you don't take F to be the set of all possible subsets is because of technical conditions. You cannot assign a well-defined probability measure if you take the event space to be the set of all possible outcomes. So after all, so ultimately, when we define a probability, we'll define it over not the sample space, but rather the event space. So for every possible event that we're interested in, what is the probability of that event happening, right? And in particular, the event space. So the event space will always include the sample space. Okay, so the event space is the set of all possible events that we're interested in, and more formally, you would have seen that the event space must be a sigma algebra. Right. So it's a collection of subsets of omega which satisfies a bunch of properties. And the third quantity, which so these three quantities together constitute a probability space. Whenever you're looking at any random experiment, these are three quantities which completely define that particular random experiment. So the third is a probability measure. Right. So and this is basically it defines a number to every possible event. So what is the probability of that particular event happening? What is the likelihood of that particular event happening? All right. So it's basically a function from which for every event you have a real number associated with it, and these real numbers lie in 0 to 1. So the smallest, so it's always non-negative, and the maximum value that the probability of an event can take is equal to 1. And this probability measure is basically a function which satisfies certain properties, and that is the probability of omega should be 1. So you also know that the probability for every event A. So for every event A, the probability of A is of course non-negative. And if you have a collection of events, A1, A2, and so on, which are all disjoint. So for every AI intersection, AJ is empty, then the probability of the union of these events, AI, is equal to the sum of the probabilities. Right, so this is, hopefully you've seen all of this in your probability course. So whenever you're talking about a random experiment, if the experiment consists of only a finite number of events, then it's pretty simple, straightforward. But then otherwise, you should really think about what these three quantities are, what the sample space is, what the event space is, and how the probability measure is defined. All right. Okay. So these are basics, and hopefully you remember what a random variable is, what continuous random variables are, what the probability mass function of a discrete random variable is, what the probability density function of a continuous random variable is, and what is the cumulative distribution function of a random variable. Okay, so the first sort of important two tool or important result in probability that we'll be using quite extensively in this course is this result called the union bound. And it's a very straightforward result, and it is the following. So if you have a collection of events, so let's say you have two events, A1 and A2 are two events. Then then you look at the probability of A1 union A2 and look at the probability of A1 plus the probability of A2. What can you say about this? Can you say that one is greater than or equal to the other, or less than or equal to the other, or you can't say anything?
Sir, RHS should be greater than or equal to LHS.
Okay.
If it is disjoint, it is equal only.
Okay, so this is less than or equal to probability of A1 plus probability of E2, and you have equality if A1, A2 are disjoint. Note that I'm saying that it's equality if they're disjoint, but it's also possible that A1 and A2 are not disjoint and yet equality holds. Can you give an example of when this might be the case? So can you come up with some example?
Sir, you mean when it is not disjoint equality?
Yes, so A1, A2 not disjoint, but equality holds.
If one event is empty, sir?
If one event is empty, okay, fine, that's true. But can you come up with something better? I want the case where neither of the events are empty. But okay, so do you know of any expression, not an inequality, but an equality for probability of A1 union A2 in terms of probability of A1, probability of A2, and something else?
So if we subtract the probability of A1 intersection A2
Okay, very good.
from
So
the
the
right.
probability of A1 union A2 is equal to the probability of A1 plus the probability of A2 minus the probability of A1 intersection A2, correct? Okay, so now is it possible for A1 and A2 to be disjoint? So which means that A1 intersection A2 is not empty, but equality still holds.
So we can move the probability of A1 intersection A2 on the left hand side. So just saying from the
Okay.
expression, sir. So in that case, like if in the case, like if we draw the Venn diagram, so in the Venn diagram, say the probability of A1 union A2 and A1 intersection A2, its sum is equal to probability of individual sums of A1 and A2.
No, that always holds, right? So you always have probability of A1 union A2 plus probability of A1 intersection A2 to be equal to probability of A1 plus probability of A2. That's all, that always holds.
So
But
what
I want
about
an example where probability of A1 union A2 is equal to probability of A1 plus probability of A2.
so what
Any
if an
example?
A1 and A2 are like subsets, like A2 is present inside A1.
If A1 is, well, that's, so then it won't hold, right? So if A1 is a subset, let's say A1 is a
Sir,
subset of A2, yes.
should A1 be equal to A2? I mean, same events?
No, so I don't want a general condition. I just want any example. Give me a particular, I don't know, random variable or a random experiment, anything. So, okay, so let me put it in a different way. If P of A1 union A2 should be equal to probability of A1 plus probability of A2, and A1 and A2 are not disjoint, then what should happen? Just look at this and tell me what should happen. So what should probability of A1 intersection A2 be?
0.
It should be 0, right? But just because probability of A1 intersection A2 is 0, it doesn't necessarily mean that A1 intersection A2 should be empty, correct?
Okay, so I think you're talking about some null set, and I think probability of
So
that null.
no, I mean null set always has probability 0, right? If A1 intersection A2 is the null set, then you're sure that probability of A1 intersection A2 will be equal to 0. But it's also possible that probability of A1 intersection A2, sorry, A1 intersection A2 is not the null set. Okay, so let's take one example. Okay, take any continuous random variable. Let's say the Gaussian random variable. Okay, let's say that X is Gaussian. Okay, and say A1 is the event that X is in the interval, say 0 to 1. Okay, again, you can come up with a whole bunch of examples, but here is one simple example. So A2 is the event that X is in the interval, the closed interval 1 to 2. Okay, so in this case, since X is a continuous random variable, fine, probability of, so you know that both A1 and A2 are not empty. What is A1 intersection A2?
Just one.
Exactly, it's just 1, right? And so probability of A1 union A2 is the probability that X is in the interval 0 to 2. So this is the probability of whatever A1 plus probability of A2. But then what is the probability of A1 intersection A2? A2 is the probability that X is equal to 1, right? But what is this equal to?
When we are taking an interval,
Yes.
like
Okay.
0 to 1 or 1 to 2, so like when we compare the discrete and continuous case, discrete case, like tossing a coin, we have like two outcomes. So
Okay.
there we can assign like that probability to that outcome, but when it's continuous, we can't assign a probability to each point because there are infinite points from 0 to 1 in the real line. So we consider the probability of a single point to be 0. We only consider intervals to assign probability when it is continuous values.
Right. So if you have a continuous random variable with a well-defined probability density function, then the probability that that random variable takes a particular value, say probability that X equal to 1, is always equal to 0. Right? Because let's say that you use whatever a random number generator to generate a Gaussian random variable. The probability that it will be equal to whatever, equal to pi or equal to 1, that is equal to 0. Right? So the only event which has a positive probability is an interval or a collection of intervals. All right. So as long as the length of the interval is non-zero, the probability will be non-zero. If the length of the interval is 0, then the probability is equal to 0. Or the length of the event, if your event can be considered as whatever a collection of line segments or a collection of intervals, then only if the length of that is greater than 0, the probability of that particular event will be greater than 0. Right? So in this case, the probability that a continuous random variable is equal to 1, this is equal to 0. But the intersection is not empty. Any questions?
So, sir, whatever
Yes.
you asked, like that equality should hold even if they are disjoint events, that is applicable only for continuous random variable.
No, not necessarily, right? You could always define an experiment where certain events take certain events take value equal to 0, so take probability equal to 0, right? So
Sir,
go ahead.
like one discrete example, can you show, sir?
I mean, so you can always say that you can always define the outcome of certain events. Sorry, you can always define the probability of certain events to be equal to 0, right? So let us say that you can always say that okay, you define some experiment. Let us say that the possible outcomes of this experiment are 1, 2, 3, 4, 5, 6, and you say that the probability of getting a 3 is actually 0, right? It's again it's kind of a trivial example. Let's say that the probability of 3 equal to 0, the probability of 1, 2, 4, 5, 6 are all greater than 0. Probability of I is greater than 0 if I is in 1, 2, 3, 1, 2, 4, 5, 6. It's again it's a simple example. It's a trivial example. But now if I say that event A1 is 1, 2, 3, and event A2 is 3, 4, 5, then the probability of the intersection is 0, even though the intersection is non-empty. Correct. So any discrete example where because ultimately, remember, you're not counting the number of elements. There are two things that you're measuring, right? One is the size of the sets, and the other is the probability of associated with those sets. Now, you could always assign a 0 probability to some set, a non-empty set. You know that the probability of every empty set is 0, but you can also have certain non-empty sets which have 0 probability, because after all, it's up to you to define what the probability measure is, right? Does that make sense?
Yes, sir. So A1 is like A1 and A2 both have 3. So like not so if I say A1 has occurred in this example, it can be that outcomes 1 or 2 had come, 3 need not come, but
Correct.
even like A2 also 4 or 5 would have come, but 3 wouldn't have come. So
Yeah.
okay. So then, sir, so when, okay, now if we take probability of A1 and you say 3 won't occur, I mean, the probability of that 3 occurs is 0. So now when I take probability of A1, I will take it as 2 by 5.
No, I don't know, right? I have not defined what the probabilities of each of those occurring is. It could be anything, right? So I could say that probability of 1 is half, probability of 2 is, I don't know, 1/4, probability of 4 is 1/8, probability of 5 is 1/16th, and probability of 6 is 1/16th. Anything, it could be any number, right? As long as the sum of the probabilities is equal to 1, it's a valid probability distribution. I can assign 0 probability to some of these outcomes. Some of them, they need not always be 1/6 or 1/5 or anything, right?
Okay, they need not be equally likely.
No, they need not be equally likely at all.
So, sir, like if 3, if we say probability of 3 is occurrence of 3 is 0, then our sample space can be limited to 1, 2, 4, 5, 6
Correct,
only.
correct. You could potentially look at a different okay. You could probably change the experiment slightly and say that my new sample space is just 1, 2, 4, 5, 6. Correct. But that doesn't mean that you cannot define this, because it is possible in certain applications. We'll maybe see some examples later on where sometimes you don't even know what the probability of what the actual probabilities are, right? So you know that, okay, so let's take the following example where let's look at English or ASCII characters, right? If you look at a text, right, let's look at ASCII text. Right. Now this could be, this contains all the English characters as well as numbers, space, special characters, and so on. Correct. Now if you look at specific sources, for example, if you look at English text, a priori you don't know whether the text is English text or something else, right? But if it is actually English text, then you know that it's only going to contain a subset of all possible ASCII characters. It's going to contain letters and spaces, punctuation marks, and that's about it, right? But there are certain other ASCII characters, certain special symbols, which you know are not going to occur. So typically something like I don't know, dollar or hash is maybe not going to occur in your ASCII text. So if you want to model that as a random source, then the probability of occurrence of certain symbols is 0, right? But still, you may want to consider it as part of your sample space because, after all, well, it's all possible ASCII text. Correct? So, for example, when you're designing a compressor, you should take into account everything. But the actual source may not produce certain characters at all. But as part of the algorithm design, you should keep that in mind. Does that make sense?
Yes, sir. Thank you.
Okay. Any other questions? Okay. So the first important tool was the union bound, which says that the probability of the union of two events, or in fact, the probability of the union of any number of events, probability of EA1 union A2, and so on, AK, this could even be an infinite number of events. This is always less than the sum of the probabilities of those events. Okay. So, but now typically I'll also want certain bounds on the probabilities of certain events. In particular, I want to know what is the probability that a particular random variable takes a value larger than a certain amount. So for that, a very generic inequality is this so-called Markov's inequality, and it says the following. So if X is a positive random variable, or it's a non-negative random variable, So again, in this case, you know that the probability that x is less than 0 is equal to 0. Okay, so x takes values greater than or equal to 0 with probability 1. Okay, so if x is a non-negative random variable and it has a finite expectation, so if the expected value of x is equal to some number mu, then the following holds. Then for any number a greater than 0, we have the following. So the probability that x is greater than a or greater than or equal to a is less than or equal to mu divided by a. So the expectation of x divided by a. Okay. Has anyone not seen the Markov inequality before? Okay. So there's Tandeep. Anyone else who has not seen Markov's inequality? Okay, so a couple of you have not seen this. Fine. So it's a good thing that we are doing this then. All right. So this is for any non-negative random variable. Remember. Okay. So let's see how we actually get how do we prove such an inequality? We are making absolutely no other assumptions except for the fact that x is non-negative and the mean of x is finite. Okay. You can also have random variables with infinite mean. So let's see how we can show this. Okay, so to prove this, we'll start with the definition of the mean. So mu is basically the expected value of x. So again, so the definition of the expectation can depend on whether it's a discrete random variable or a continuous random variable. So let's assume that x is continuous. Okay, you can again do the same calculations when x is discrete. So if x is a continuous random variable, then how do you define the expected value of x? So if x has, say, a probability density function fx.
Integral of x fx dx.
Okay, so it's integral of
f of x, x f of x.
Yes, so it's x times, let's say, fx
dx.
Dx, right?
From
And what are the limits of integration?
minus infinity to infinity.
Okay, so in general, it's going to be minus infinity to plus infinity, but in this case, what is it going to be?
8.
Correct. So it's 0 to infinity, right? Because you know that x is going to be greater than or equal to 0 with probability 1. Okay. So this is the expression for the expectation. Now, what I'll do is I'm going to split this integral into two parts. So what I'm interested in is the probability that x is greater than or equal to a. So I'll split this integral from 0 to a, x times fx of x dx plus integral a to infinity of x times fx of x dx. Okay. So what I want is an upper bound on this. So I'll say that, can I say that this is greater than or equal to only the second term? Is this true?
Yes, sir.
It's always true, right? So you know that you're integrating from 0 to a, so it's non-negative. X, so therefore x is greater than or equal to 0. Fx of x is a probability density function, so it is always greater than or equal to 0. So this integral is going to be greater than or equal to 0. Right? So this quantity is greater than or equal to 0. So therefore this mu is going to be greater than or equal to only the second term. Okay, good. Now in this, since I'm integrating from a to infinity, x is going to be always going to be greater than or equal to a. All right, so can I say this? This is a fx of x dx. So this is a integral a to infinity fx of x dx. All right, but this is a times, what is this quantity? Integral a to infinity f of x dx.
A probability of x greater than a.
Exactly. So this is just the probability that x is greater than or equal to. Correct. So I have mu to be greater than or equal to a times probability. So mu is greater than or equal to a times the probability that x is greater than or equal to a. Or if I take a on the other side, I have mu over a is greater than or equal to probability that x is greater than or equal to a, or probability that x is greater than or equal to a is less than or equal to mu over a. Okay. So it's a simple inequality. Proof is simple. We've used this a little bit, just a couple of tricks. Okay. Any questions so far?
Sir,
Yes.
this inequality, how is it going to help?
Okay, so we'll see that. So I'll use this inequality to derive more complicated inequalities. So the Markov's inequality in itself is not very much used. There are certain applications where you might want to use it, but then I'll use this to derive a bunch of other inequalities, and then we'll see how that can be useful. Okay, so bear with me for a while. So I'll derive a bunch of these things. So in particular, if you know what, so one reason why we use these inequalities is that in many applications we cannot compute exact probabilities. So we'll see that very soon we'll want certain probabilities. So in particular, so we'll be interested in deriving bounds on quantities of the following form. What is the probability that x minus the mean of x is greater than or equal to some alpha? Okay. So one example is the following. Let's say that I toss a coin 100 times. Okay. Let's assume that it is a fair coin. If I toss the coin 100 times, then I know that on average, roughly 50 times I'm going to get a head, and roughly 50 times I'm going to get a tail. Correct. So this we know, we have an intuition for this particular experiment. But then, what if I want to know something like, what is the probability that the number of heads is going to be exactly equal to 50? Now that's going to be very small. It's not going to be very large. But what is the probability that the number of heads is going to be roughly 50? So maybe between 45 to 55, right? Now, what is the probability that the number of heads is between 45 to 55? Now I can try to compute it by hand. I can derive a really complicated expression for this and then try to evaluate it. But that's very, very difficult. So instead, if all I want is an upper bound on this particular probability, then it turns out that I can get it. And for that, I'm going to use these inequalities. And so these inequalities, so all of these, the next couple of inequalities that I derive are what are called concentration inequalities. So what they say is that if you look at this particular quantity, right, the probability that x is very close to the mean, it turns out that for many random variables of interest, this probability is going to be high. Now, if you look at a single random variable, it is not, again, it may not be very useful. But then if you look at sequences of random variables, for example, I'm tossing a coin 100 times, or I'm generating 100 Gaussian random variables, and I want to know that how far the average of these random variables is close to the true mean. Right? So it turns out that this probability is very high. So these random variables concentrate very tightly around the mean, and we can get very good upper bounds on these probabilities using such concentration inequalities. Okay, so that's the high level motivation, and we'll explore this in some detail. In fact, a lot of information theory is boils down to this very specific fact that certain random variables concentrate about their mean, and we'll be interested in certain random variables or certain random sequences, and basically that which basically forms the crux of almost everything that we see in information theory. Any questions?
Sir? So that is greater than or equal to alpha, or less than or equal to?
Whatever. If you have one, you have the other, right?
I mean, if random variable is close to mean, then if you are measuring that, then it is less than or equal to alpha.
Correct. So, yeah, but then the probability that this quantity, so it's greater than or equal to alpha, is simply 1 minus the probability that this mod is less than or equal to alpha.
Okay. Okay.
So I'm going to get an upper bound on this particular probability, which means that I'll get a lower bound on the probability that mod x minus expectation of x is less than or equal to alpha. Okay, good. Any other questions? Okay. So maybe before I proceed to the next particular inequality, let's have a very quick quiz. So this will just be like 2-3 minutes and very simple questions. So this will be assigned on Google Classroom, but I'm going to give you, put the link in the chat box over here. So just let me know if you haven't got the link, because you should be able to see it in the chat box now. So maybe you can take a minute more.
Sir, I submitted the quiz, but when I look at the classroom, I'm not seeing any work assigned there for me.
Oh, that's fine. I mean, shouldn't be.
Because I submitted the quiz, I just checked the quiz one link in the classroom.
Okay.
Like, there's nothing is shown as there's been submitted, or like it's just showing me assigned. That's it.
That should be fine. I mean, so basically, I'm just collecting the responses and I'll grade it separately. So that's not an issue.
So 1 more minute, can you give me 10:55?
Okay, 1 minute. It's a simple thing. Is everyone done? Anyone yet to submit?
Sir, from the link you put in the chat box, I
Yes.
opened the form and submitted. But classroom, is it okay? Like, there also, the form is like.
Should be fine. I mean, it
Okay.
should anyway record your score. That's it. As long as you filled in the form, whether it's through classroom or here, it shouldn't matter.
Okay, sir.
Okay, so hopefully everyone is done. I'm going to stop accepting responses. Okay. All right. So again, there were two questions. One is what are the compressed file sizes for F1 and F2 if F1 has roughly 50-50 number of zeros and ones, and F2 has more number of ones than zeros. So the compressed file size for F1 should be larger, right? And the second question was, if X is a Bernoulli point to random variable, then what is the expected value of X? The expected value of X is just going to be 0.2. Right? Okay, so all right, so let's continue. So we saw one inequality, which was Markov's inequality. Now we're going to use the Markov's inequality in itself is not useful, but then it can be used, although it's not the best inequality, you can use it to derive much more general inequalities, much more powerful inequalities, which we use a lot. So the first thing that we see is the so-called Chebyshev inequality. Now Markov's inequality is valid only for non-negative random variables. Right? So what if the random variable is not non-negative? So So the Chebyshev inequality says the following. So if x is any random variable, it could be continuous, it could be discrete. If it has a mean mu, which is finite, and variance equal to, let's say, sigma square, which is also finite, then you take any positive number a, the probability that the absolute value of x minus mu is greater than or equal to a is less than or equal to sigma square divided by a square. Okay, so the probability that x deviates from its mean by an amount of a is less than or equal to sigma square by a square. So if you look at a plot of the graph, then so you know that x can maybe be any real number between minus infinity to plus infinity. Now you look at a particular amount a, all right, so this is distance a. So what is the probability that x lies in this particular interval, mu minus a to mu plus a? Now this Chebyshev inequality says that it's at most sigma square divided by a square. Okay. So note that let's first look at this inequality. Note that this is not very useful if I take a to be less than sigma, right? If I take a is less than sigma, then the right hand side is going to be some quantity which is greater than 1, and you know that the probability of any event is always going to be less than or equal to 1. So this is really useful to look at what I call tail events. So when a is very, very large, then this quantity on the right hand side is very, very small, so this bound is also more useful. For example, if I look at a Gaussian random variable, right, so with maybe 0 mean, then and I pick some really large point, say 100, right? So what is the probability that x minus mu, x is greater than, say, mu plus 100, right? X is greater than 100, or it's between it's less than minus 100 or greater than plus 100. Then this bound becomes useful because sigma square is something maybe 1 or 2, and a square is 100. So 1 divided by 100 square is something very, very small. Okay, so let's do a very quick proof. I won't. It's fairly simple since we already know Markov's inequality. So we apply Markov's inequality on the following random variable. Yes.
This is sorry to interrupt.
Yes.
Sir, we have a class at 11. If you don't mind, can we continue next class?
Okay, sure. Oh, it's fine.
Thank you, sir.
Okay, so we'll continue in the next class. So see you then. I've already uploaded some notes, lecture notes, on both on Google Classroom as well as the website. So just take a look.
Thank you, sir.
Okay, thank you.
Sir,
Yes.
may I ask about the quiz?
Yes, please.
Yeah, according to the previous lecture, we have taken that the expected value of some random variable is going to be the probability of this variable multiplied by logarithm 1 divided by this probability. So
no, that is the entropy of the random variable, right?
Oh, okay, yeah.
So the expected value is just expected value of some random variable. Is if it's a discrete random variable, then you sum over all possible outcomes is x times p of x. Right? In the case of the quiz example, it would be 0 times the probability of 0 plus 1 times the probability of 1. This is 0, so it is 1 into 0.2.
Okay, sir. Thank you.
Any other questions?
No, thank you, sir.
Okay. Okay then, so we meet in the next class. So see you all until then. Yes. Yes. Okay. Yep. Thank you.